Today we are going to look into some other concepts in kinetics. Okay. So, last class we had done till the concept of Cauchy stress tensor, and today before going into proof that Cauchy stress tensor is an objective quantity, and I will come to it what is meant by objective. First, let us study and understand the effect of rigid body motions and what is meant by objectivity. Okay. So, the title of this slide, as you can read, is effect of superimposed rigid body motions and objectivity. So, before we discuss and dwell into the mathematical details, physically what can happen during a deformation when you are going from say one time instance to another time instance. Okay, the body is deforming. Okay. Now, there might be situations that the body between two time steps may undergo no deformation and only rigid body rotations, okay, or rigid body translations. It may also so happen that going from one time instance to another, the body may undergo rotations, translations, both rigid body as well as some deformation. Okay. Now, you can very well understand that when a body undergoes rigid body motion, that is rotation or translation, the body cannot develop stresses. Okay. There will be no deformation. So, no deformation means the body cannot develop any stresses. Okay. So, how do we deal with these kind of situations? Okay. So, we will focus only on the current subject, which is focus more on solid mechanics part. Okay. So, objectivity is a very important issue in solid mechanics. Okay. Now, you can understand and explore the concept of objectivity by studying the effect of a rigid body motion which is superimposed on the deformed configuration, as shown in the figure. Okay. Now, you see at time t equal to 0, the body is occupying a certain configuration B 0 bounded by surface del B 0. Okay. And you have a material vector dx at point P. Okay. Now, as the body undergoes deformation given by this deformation mapping psi, okay, so it occupies a volume in space B bounded by surface del B, okay, at time t. That is the configuration that the body is occupying, and this material vector deforms to this spatial vector dx. Okay. Now, till now what we have considered is between t equal to 0 to t equal to t, the body has undergone purely deformation. There is no rigid body motion, but practically in physical situation you may have the body undergoing deformation as well as rotation. Now, as I said earlier, the stresses can be developed only because of deformation, okay, not because of rotation. So, let us say we had the final configuration. Okay. So, we had the final configuration which is shown here. Okay. So, this is obtained. So, this shaded region, okay, is obtained. Okay. So, this is also at time t, okay, but this final configuration is actually what is called the deformation plus rotation equal to this is your final configuration. Okay. Now, between this intermediate configuration and this final configuration, you had body undergoing pure rotation, okay, which is a rigid body motion. Therefore, there should not be any stresses develop inside the body. Okay. So, let Q be the transformation or the rigid body rotation tensor, okay, which causes this body at time t to rotate and occupy this position. So, the body is occupying the position configuration B tilde. Okay. So, tilde above a symbol we will put tilde to show that that quantity is obtained by taking rotation, okay, and del B tilde is the surface, and then this vector dx deforms to dx or rotates to dx tilde. Okay. Now, between the reference configuration, okay, and the current configuration, that is this intermediate, for example, this vector has changed its length. Okay. So, dl, d capital L goes to d small l, but when the vector rotates, when this vector dx rotates, the length of the vector, let us say dl tilde, will be same as the length of the vector before the rotation, because rotation does not change the distance between any two points. Okay. Let us now try to put things in mathematical framework. Okay. So, as I have written here, when a body undergoes rigid body motion, there are many quantities that describe the behavior of the body will remain unchanged, okay, which means to describe the behavior of the body we have many quantities, okay, like for example, we have Green Lagrange strain tensor, we have Wright Cauchy Green tensor, there are many such quantities and these quantities will remain unchanged. Okay. Now, for example, one such quantity is the distance between 2 points. Okay. The another quantity is the state of stress at a point. So, these are the quantities, for example, that will not change, okay, because there will be no new stresses which are generated, that the state of stress at a point which and state of stress we defined in the earlier discussions, these quantities will not change. Okay. So, such quantities are what we refer to as objective quantities. Okay. So, now due to this superimposed rigid body motion, the spatial description of these quantities may change. As you saw in the picture that we had in the previous slide, dx, the spatial vector dx rotated and became dx tilde. So, that means the spatial description has changed, but what has not changed are some of the intrinsic nature of these quantities. Okay. So, what is the intrinsic nature of that vector dx? It is the length. So, the length which is given by dx dot dx and taking a square root we get the length. Now, that quantity has not changed, which means if I take dx tilde dot dx tilde and then take the square root, I should still get the same length dl. Okay. Although my vector dx has changed to dx tilde, that is its spatial description has changed, but the intrinsic nature of this quantity which is dx has not changed. Okay. So, as I stated earlier, study of objectivity is important during the description of deformation, since rigid body motion do not cause stresses to develop. Okay. So, when the body undergoes rigid body motion, there will be no stresses generated inside the body, and this we have to ensure that when we are doing our numerical computation, and during that numerical computation, if the deformation, total deformation of the body is composed of say stretch plus rotation, these stresses are computed only because of stretch, not because of rotation. Okay. So, how we will do that is we are looking here. Okay. So, now to develop the mathematical framework, we consider an elemental vector dx in the initial configuration that deforms to the spatial vector dx in the current configuration. Okay. So, we already know the spatial vector dx is the deformation gradient times the material vector dx. Okay. So, this we already had seen. Now, when the body undergoes rigid body rotation, okay, for simplicity just take the motion is composed of rigid body rotation, then this spatial vector dx is rotated to another spatial vector dx tilde. Okay. So, as I shown in the figure, dx rotates to spatial vector dx tilde. Okay. Then the relation between dx and dx tilde is given by dx tilde is q dx, where q is a orthogonal rotation tensor which rotates dx to dx tilde. Okay. Now, I can use equation number 42 for spatial vector dx, and then I can write q dx as q f into material vector dx. Okay. Now, I can write q f as f tilde. Okay. So, what I am doing is q f I am writing as f tilde. So, this is the deformation gradient tensor which takes me from the initial configuration to the final rotated configuration. Okay. So, q here is an orthogonal rotation tensor which describes the superimposed rigid body rotation. Okay. Now, as I stated earlier, we can clearly see that the length of the vectors dx and dx tilde will remain unchanged, because we are just taking the vector, okay, like this pen, and we are just rotating it by a certain angle. Okay. So, now when you just rotate, the length of this pen, for example, that vector dx will not change. Okay. What it means is mathematically dx tilde dot dx tilde, okay, should be same as dx dot dx. Okay. So, dx tilde is nothing but q dx. Okay. So, this is q dx. So, q dx dot q dx, and that I can write as the first quantity. I can open up the bracket because A dot B is A transpose B, and A here is A q dx. So, I can write the first quantity in the bracket as dx transpose q transpose q dx. Okay. Sorry. So, this has to be q dx. Okay. Now, because q is a orthogonal rotation tensor, so q transpose is identity. Once I have that, I can write dx transpose dx, which is nothing but dx dot dx, and I can indeed see that the length of the spatial vector remains unchanged. Okay. So, remember QF is F tilde. Okay. This relation we will use. Okay. Now, therefore, in this particular sense, we say that the vector dx is an objective quantity under rigid body rotation. Okay. So, this intrinsic nature of this vector, which is its length, remains unchanged. Okay. So, this definition we can now generalize and say anything, any vector A which transforms according to the relation given by equation number 45, which is A tilde is q A, okay, and A tilde is the vector in the rotated configuration, q is the orthogonal rotation tensor, and A is the spatial vector. Now, any vector A which satisfies this condition will be an objective tensor. Okay. So, any vector A which transforms according to the above relation when undergoing rigid body rotations will be called an objective vector. Okay. So, whenever we have a relation and we say a certain vector is an objective vector, then this relation number 45 will be satisfied. Okay. For example, now consider the velocity v, which is given by del psi by del t, or we can also write del x by del t, where x is psi x comma t. Okay. So, this we have already seen, and let us inquire whether velocity vector is an objective quantity, okay, is an objective vector. So, if velocity vector is an objective vector, then surely it should follow equation number 49, which means v tilde should be equal to q v. So, under rigid body motion, the velocity vector should transform according to this particular relation. Now, let us see whether we get velocity vector as a objective quantity. Okay. So, under rigid body rotation, v tilde will be nothing but d psi tilde by dt. Okay. Now, psi tilde is nothing but q psi. Okay. So, this we have already shown between the, or not we have already shown, but in the figure if you see on the right hand side there was this relation. So, going from, so this was psi and this was q. Okay. So, this was psi tilde and this was time t equal to 0 and this was the rotated. So, psi tilde will be equal to q psi. Okay. Now, if we substitute psi tilde as q psi, we get v tilde as del by del t of q psi. Now, I can open up the brackets and take the derivative, and what I get? I get two terms, q del psi by del t plus q dot psi. Okay. Now, because of the presence of this second term which is shown here, okay, this is the second term. Therefore, we wanted to show that if velocity vector is an objective quantity, it should transform according to this relation, v tilde is q v, but what we are getting, v tilde is q v, because this is your v, q v plus q dot psi, okay, which is indeed not equal to q v. So, therefore, we can say that v tilde, the norm of v tilde is not same as the norm of v, which means that because of the presence of the second term in the velocity vector is not an objective quantity. Okay. Therefore, now moving to second order tensors. Okay. So, before we move that further, you notice that we have said the deformation gradient tensor, which it takes you from the material configuration to the final rotated configuration, that is f tilde is equal to q times f. Okay. Now, we can show that the material tensors, that is right Cauchy Green tensor and the Green Lagrange strain tensor E, they will remain unchanged by the superimposed rigid body motion. So, let us start. We know the relation of the right Cauchy Green tensor, which is nothing but f transpose f. Okay. Now, C tilde would be f tilde transpose f tilde. Okay. So, that is how we proceed to show that any quantity is an objective quantity. Okay. So, whatever may be the relation, what we do? We write that relation with a tilde over it, so that becomes an expression in the rotated configuration, and then we will try to produce the objectivity statement. Okay. Now, f tilde from equation 47 we see is q f. So, we get q f transpose q f. Okay. So, the first transpose A into B transpose is nothing but B transpose A transpose. So, I get f transpose q f, and I know that q transpose q is an identity tensor, because q is a orthogonal tensor. Okay. Because q is an orthogonal tensor, q transpose q is I, therefore, what I get is f transpose f, and I know f transpose f is nothing but C. So, what I have shown, the right Cauchy Green tensor is nothing but C is equal to C tilde. So, indeed the material tensor C remains unchanged. Okay. Similarly, I know that C, okay, so C is not 2E, okay, so E is 1 by 2 C minus I, okay, so 2E plus I equal to C, okay. Okay, so there should be I here, okay. So, C equal to 2E plus I, and I can show, because C is equal to C tilde, I can show E tilde is E, or also the Green-Lagrange strain tensor, okay, is an objective quantity. It does not change with rigid body motion, okay. Obviously, because these things are defined in the initial configuration, so they will not have any effect when you rotate the spatial configuration, okay. Now, however, we can show that the spatial tensors transform according to different relation, okay. We know that B, that is the stretch tensor, is equal to F transpose. Now, writing this in the rotated configuration, we write B tilde is F tilde F transpose. What does it make? F tilde is given by equation number 47. So, I can write Q F into F Q transpose, okay. Okay. And then I take the A B transpose, B transpose, A transpose. So, I get F transpose, Q transpose. Okay. Now, this middle term over here, F transpose is nothing but B. So, I get B tilde as Q B Q transpose. Okay. Similarly, I can show that E tilde will be Q E Q transpose. So, this is to show that indeed E tilde is Q E Q transpose. You know the relation for E, E is nothing but 1 by 2 I minus B inverse. Okay. So, E tilde will be I minus B tilde inverse, okay. And then B tilde relation you already know from here, you just substitute and you try to show, okay, that you get the following relation, okay. And this Q I will be Q Q transpose, okay. So, you can take Q from the left hand side, Q transpose from the right hand side, and you can show that the Euler-Almansi strain tensor transforms according to the following relation, okay. Now, it seems there are these tensors B tilde, I mean B and E are not objective, but we said the spatial description may change, but their intrinsic value or intrinsic nature of these quantities will not change. As you can see from expression over here, B tilde is Q B Q transpose. So, the tensor itself has changed, but now let us show that what has not changed. Okay. Now, although say E tilde is not equal to E, but we know that the intrinsic change in length they represent remains unchanged. Okay. You remember from our discussion in kinematics that the half of the change in the square length of the final element, okay, the element in the current configuration minus the square of the length of the element in the reference configuration is given by dx dot E dx, and this I can show that it is indeed equal to dx tilde dot E tilde dx tilde. Okay. To show that, I can start from here, okay, and dx tilde is nothing but q dx. And what is E tilde? E tilde is q E q transpose, and then dx is q, dx tilde is q dx. Okay. So, I am just trying to show that indeed this quantity is equal to this quantity. Okay. So, now I can write q dx dot q e q transpose q dx. Now, q transpose q is identity. So, I can write q dx dot q e dx. Let us not put double under bar, okay, it is clear from the context. So, now I can write this as dx transpose q transpose q e dx. Q transpose q is identity. So, this is dx transpose e dx, which means this is nothing but dx dot e dx. Okay. So, therefore, although the Euler-Allemasi strain tensor has changed, that is its spatial description has changed, but the intrinsic nature of this tensor, which is given by the difference of the length, square of the length, has not changed. Okay. Therefore, E tilde, okay. So, E tilde given by q e q transpose will be called an objective quantity. Okay. So, therefore, E tilde or rather E is an objective tensor. Okay. So, this we can generalize to any second order tensor S. Let us say S is a second order tensor in the spatial configuration. Therefore, if this tensor transforms under rigid body rotation according to equation number 53, okay, which is S tilde is q s q transpose, then this second order tensor S will be called a objective tensor. Okay. That will be called an objective tensor. There will be a lot of second order tensor. One of the most important is the Cauchy stress tensor, and therefore, we have to later on show that Cauchy stress tensor is indeed an objective tensor. That will show in the coming slides. Okay. So, thus any second order tensor which transforms according to the relation given by equation 53 will be called an objective tensor. Okay. So, an objective second order tensor transforms according to this relation under rigid body motion. Okay. Therefore, naturally stress and strain tensor which are used to describe the material behavior under external loads need to be objective tensors. Okay. That is why, because the product of stress and strain gives you energy, and when the body undergoes rigid body motion. So, the internal energy which is there as a product of stress and strain should not change, okay, but the physical, okay, or the spatial description of these tensors which is stress and strain tensors will change. Therefore, if these tensors are objective, then the intrinsic nature of these tensors, which is nothing but the internal energy, will not change, which means there will be no new stresses generated inside the body because of the rotation. Okay. Now, let us consider a case of a non-objective second order tensor. Okay. Let us consider the velocity gradient tensor. Now, we know that the material time derivative of the deformation gradient tensor was given by LF, okay, F dot is LF. Therefore, L is nothing but F dot F inverse, and let us investigate whether the velocity gradient tensor is an objective quantity. It is not an objective quantity, and we will show it. Now, let us write the velocity gradient tensor in the rotated configuration. Okay. L tilde is F tilde dot F tilde inverse. Okay. Now, we know that F tilde is Q F. Okay. F tilde is QF, therefore, I can substitute this here, and if I do simplification, okay, this I leave it to you, I will get L tilde SQL Q transpose plus Q dot Q transpose. Okay. Now, if velocity gradient tensor L was an objective quantity, L tilde should transform according to this relation. Okay. Because L is a second order tensor, it should transform according to this relation. But when we see this expression over here, we see that we have this second term, okay, which is Q dot Q transpose, which in general will not be equal to 0. Okay, it will not be equal to 0 tensor. Therefore, since we are not getting this relation, therefore, the velocity gradient tensor is not an objective quantity. So, this is not equal to QL Q transpose, therefore, the velocity gradient tensor is not an objective quantity. Okay. We can show that the rate of deformation tensor, okay, d, which is nothing but which is the symmetric part of the velocity gradient tensor. Okay. D is L plus L transpose by 2. We can show that indeed the rate of deformation tensor d is an objective quantity, which means d tilde transforms, d transforms according to the relation d tilde is q d q transpose. Okay. And how do you show that? You already know that L tilde transforms according to this relation q L q transpose plus q dot q transpose. Okay. So, you know d is the symmetric part, you can write d tilde as 1 by 2 L tilde plus L tilde transpose, and from equation 56 you can substitute the value of L tilde here, and then you can simplify to get the following expression. And then you can show that this quantity in the bracket here, the second quantity is equal to the 0 tensor. How to show that? I leave it for you as an exercise. Okay. It is very simple to show. If you show that this is equal to 0, then d tilde is q d q transpose, and therefore, the rate of deformation tensor is an objective quantity. Okay. Now, coming to the specific topic of stress objectivity. Okay. Stress tensor, the Cauchy stress tensor is an second order tensor. Okay. And now, let us inquire whether this Cauchy stress tensor is an objective tensor or not. Okay. Since it is a spatial tensor and it will be used in the equilibrium equation, therefore, and this equilibrium equation we will see in the coming slides. Okay, how we will get that expression? It will contain the Cauchy stress tensor. Okay. So, now it is essential that we investigate whether the Cauchy stress tensor is an objective tensor. Okay. So, now you have this body, okay, let us say you had this body and you cut it open. Okay. So, you had the body was under the action of certain externally applied tractions, because of that the body has developed certain stress. Okay. So, at a spatial location x, okay, at point P, when you cut it open, let this be area dA, which is characterized by normal n, and let T be the traction at this point. Okay. So, T is the traction at this surface, okay, given by the T equal to function of normal n. Okay. Now, let us see if we give a rigid body motion. Okay. Now, if we give superimpose rigid body rotation using the transformation tensor Q, orthogonal transformation tensor Q, your spatial description of the normal and the traction vector will change to n tilde and t tilde, okay, and the current position, spatial position of the point is x tilde. Okay. So, then as I said here, the transformation of the normal vector n and the traction vector t under this superimposed rigid body rotation will be given by t tilde is q t and n tilde is q n. Okay. Now, because n and t are objective vectors, therefore, t tilde is q t and n tilde is q n. Okay. This you can show that the length of n tilde will not change and also t will not change. Therefore, t tilde and t and n are objective quantities and are given by 57 and 58. Okay. Now, we know from Cauchy stress principle that traction at a point, okay, traction on a plane whose normal is n is given by sigma times n, where sigma is the second order Cauchy stress tensor. This we had derived, okay, in equation number 40 in the previous slides. Therefore, now to investigate whether sigma is an objective quantity, let us write equation 59 in the rotated configuration, and this is written as t tilde is sigma tilde n tilde. Okay. Okay. So, what we have done? We have just written, put a tilde over each quantity in equation number 59. And now, we have been given that traction vector t and the normal n are objective vectors. Therefore, what we can do is substitute equation number 57 and 58 from the previous slides in equation number 60. Okay. And what we get? Q t is sigma tilde q n. Okay. This is what we get. Okay. Now, from equation 59, I can see that traction vector t is nothing but sigma n, and that is what I substitute here. Okay. So, I can put equation number 59 here and I get q sigma q n is equal to sigma tilde q n. Okay. Now, if you notice, we have n on the right hand side, on both the left hand and right hand side, and n is present in both the expressions on the left hand and right hand side. Therefore, this implies that q sigma is sigma tilde q. Okay. And now, if I just post multiply both sides, okay, of the equal to sign by q transpose, okay, I get q sigma q transpose as sigma tilde q q transpose. And because q is an orthogonal tensor, therefore, q q transpose is identity, which means this quantity over here becomes identity. Therefore, sigma tilde I will be equal to sigma tilde. Okay. So, therefore, I get sigma tilde is q sigma q transpose, and if we match this expression, compare this expression with our expression for the objectivity of any second order tensor, which is S tilde is q S q transpose, we see that equation number 61 matches with the expression that we had in the previous slides. Okay. Therefore, since this expression is the expression for a objective tensor, therefore, sigma or the Cauchy stress tensor is indeed a objective tensor. Okay. So, which shows that, and this if we compare with this expression, that is what I said, we see that Cauchy stress tensor is indeed an objective tensor. Okay. That we have shown. Okay. And therefore, what this means is Cauchy stress tensor is a valid candidate in the description of the material behavior. Okay. So, we can use this tensor in describing the material behavior under the action of external loads. However, we should remember, okay, and we will see it later, that the material rate of the Cauchy stress tensor, okay, the rate of change of Cauchy stress tensor, which is sigma dot, that quantity is not an objective tensor. Okay. So, Cauchy stress sigma is objective, but the rate of Cauchy stress sigma dot is not an objective quantity. Okay. So, I cannot use sigma dot to compute the increment in the stress. So, sigma dot is nothing but sigma dot into dt will be equal to d sigma, and in case of finite time interval sigma dot delta t will be equal to delta sigma. So, if I have to compute the increment in stress between two time steps, I cannot simply write sigma dot delta d to get the increment in the Cauchy stress, because sigma dot is not an objective quantity. Okay. So, I have to come up with some other objective stress measures that we will see in the next module, towards the end of next module, where we will discuss a lot of objective stress measures. Okay. So, let us now move to the topic of equilibrium equation. So, now we have shown the Cauchy stress principle, and also we have shown that the Cauchy stress tensor is an objective quantity. Okay. So, to derive the equilibrium equation, first we consider the translational equilibrium. Okay. That is the conservation of the linear momentum. Okay. So, earlier we have derived what was called the global form of conservation of linear momentum for a deformable body. Now, what we want to do is we want to derive the local form of the equilibrium equation at any point x in the body, okay, and this we can obtain by considering the balance of linear momentum. So, remember earlier we had derived what is called the global form of balance of linear momentum, okay, and that was given by the volume integral of the inertia forces should be equal to the volume integral of the body forces plus the surface integral of the external applied tractions. Okay. So, this was already derived in equation number 29, okay. And then for static problem, this, and in this course we deal with static problem only, because if you consider inertia, there is an additional term for time which comes and which needs time integration, and because of the number of lectures being fixed, we do not dwell into the dynamic problems. Okay. We only deal with static problem. Therefore, the left hand side is equal to 0 vector. Therefore, the volume integral of the body forces but the surface integral of the traction will be equal to 0. Now, from the Cauchy stress principle, I know that traction is the traction at a point P, okay, on a plane whose normal is n is given by sigma into n. Now, if I use this in equation number 62, okay, in the second term I can put T equal to sigma n. So, what you get, the volume integral of the body forces plus the surface integral of sigma n dA should be equal to 0. Now, remember, now I can apply the Gauss divergence theorem on the second term. Okay. So, Gauss divergence theorem says that divergence of a vector field f integrated over the volume is same as, okay, so this is P del B f dot n dA. Okay. So, divergence of the vector field f over the volume can be related to f dot n dA integrated over the area. So, I can convert a volume integral to a surface integral. Therefore, this surface integral can now be converted to a volume integral which is given here. Okay. So, we have sigma n, which is nothing but something like sigma dot n, it is also sigma dot n. Okay. So, I can write divergence of sigma. Okay. So, I now have the volume integral of the body forces plus the volume integral of divergence of Cauchy stress tensor should be equal to 0. Okay. Now, I can collect both the terms inside one bracket and rearrange to get the volume integral of the quantity divergence of sigma plus the body forces per unit volume times the volume equal to 0. Okay. Now, this relation 65 is valid for all volume, which means that the integrand should be equal to 0. So, this is the integrand, okay, and this integrand should be equal to 0 for equation number 65 to hold, which means that we just simply put divergence of sigma plus b equal to 0, and this is called the local form of the spatial balance of linear momentum. Okay. So, the previous expression that we had here, okay, equation number 29 was the global form, and here equation number 66 is your local form. Local because it is valid for any point x which belongs to the current configuration. Okay. So, that is the direct notation, and in the initial notation I can write sigma I j comma j, this is the divergence, plus b I equal to 0. Okay. So, that is the local form of the balance of linear momentum in the spatial configuration. Okay. So, equation number 66 is also called the stress equilibrium equation or the local spatial equilibrium equation or simply equilibrium equation. If we had inertia forces also, it would have been called equation of motion. Okay. Now, in the context of finite element literature, equation number 66 is also called the strong form. Okay. So, this equation over here is also called the or referred to as the strong form. Okay. Strong form, this is because this equation number 66 has to hold for all points x belonging to the current configuration, and there are infinite number of such points. So, this equation given by 66 has to hold for all points, and also in the context of displacement based finite element method, the continuity requirement on the approximation for displacement is higher. Okay. We will come to it later. Okay. That is why it is called the strong form. Okay. So, the continuity requirement, if you use displacement based finite element, if you directly want to solve the strong form, the continuity requirement will be 2. Okay. That is why we need to develop the what is called the weak form, and that we will do in the next few slides. Okay. So, next we move to what is called the rotational equilibrium. Okay. So, till now we have seen translational equilibrium. Now, we move to rotational equilibrium, and let us see what does rotational equilibrium, which means the law of conservation of angular momentum, what does it has to imply vis a vis the Cauchy stress.